Welcome to The Explainer. Today, we're looking at something absolutely fascinating. We're going to explore how artificial intelligence is stepping out of the virtual world and right into the physical streets we walk on every single day. As our modern cities face increasingly severe, real-world climate crises, AI is stepping up to act as a vital digital nervous system for our urban centers. It's not just about smart gadgets anymore. It's about survival, resilience, and completely transforming how a city breathes, reacts, and recovers.
Okay, let's dive right into this. We're going to follow the chronological timeline of a disaster life cycle. First up, digitizing the microclimates. Second, predicting the unpredictable. Then, optimizing emergency response. Number 4 is rapid post-event assessment. And finally, number 5, the circular economy.
So, Phase 1, digitizing the microclimate, mapping the invisible. This is all about the peacetime phase. Cities have to model and deeply understand their unique vulnerabilities before a storm even thinks about gathering on the horizon.
To really get this, I want you to picture something. Imagine stepping out on your own neighborhood block in the middle of a summer afternoon. You know that feeling when you can practically feel a stifling, unnatural heat radiating right out of the asphalt and concrete? Well, experts call that the urban heat island effect. Our cities basically trap thermal energy, creating these highly localized, complex microclimates that are drastically different from rural areas just a few miles down the road.
And the impact of this, it's huge. This heat island effect can actually raise your local city temperatures by up to an astonishing 10 degrees Celsius. 10 degrees! That is absolutely massive. We're talking the difference between a slightly uncomfortable afternoon and a deadly public health crisis during a heat wave.
But here's where the solution comes in: an AI-powered urban digital twin. Think of it like a hyperlocal, three-dimensional model of the city that maps actual heat and wind flow in real time. By utilizing these proactive AI models, city planners can instantly spot which specific blocks are trapping the most heat. That allows them to proactively roll out cool roof zoning regulations or strategically placed green spaces and trees exactly where they'll drop the citywide energy demand the most.
Now you might be wondering, how does the AI actually know what's happening on the ground? It's all about multimodal data integration. These systems act as the city's sensory organs. Up above, you've got orbital satellites constantly monitoring canopy cover and sea level rise from space. Down below, you have ground-level IoT sensors acting as the nerve endings, continuously feeding real-time data on humidity, air quality, and traffic flow right back to the central brain.
And the leap in capability we're seeing here is just wild. For decades, traditional physics models hovered around a 65% accuracy rate. They were slow and honestly often imprecise. But today, AI hybrid models have completely shattered that baseline, jumping to a 92% accuracy rate. And even more incredibly, they process this information 100 times faster than the old systems.
When you connect that processing speed directly to your own street, that's where the magic happens. Because it's 100 times faster, these high-resolution AI models can simulate over 1,000 different flood scenarios every single minute. It acts like a digital stress test for your city. It finds hidden structural vulnerabilities and pinpoints exact drainage choke points before a single drop of rain ever falls from the sky.
Moving on to Phase 2, predicting the unpredictable, early warning 2.0. This is the impending threat phase, where the city's digital nervous system actually detects the danger rolling in.
There's a fundamental shift happening here, from reaction to prediction. Traditional early warning systems, like tornado or tsunami sirens, they're inherently reactive. They sound the alarm when the danger is practically knocking on your door. AI-driven detection, however, is entirely proactive. Because it processes millions of data points all at once, it uses pattern recognition to detect extreme atmospheric pressure drops or microscopic seismic shifts hours before a human being could ever perceive anything is wrong.
And the AI doesn't just, ring a bell and call it a day. It takes immediate action. Automated safety protocols kick in instantly. It sends hyperlocal, targeted mobile alerts specifically to the neighborhoods in the direct path of danger. It initiates automated safe shutdowns of critical infrastructure, like power grids or water valves, to stop cascading failures. Plus, it generates predictive evacuation routing, utilizing live traffic data to guide citizens safely out of the city without causing total gridlock.
Phase 3, optimizing emergency response, the golden hour. The alarm has sounded, the crisis is live, and absolute urgency is the name of the game. If we look at the standard disaster lifecycle map, mitigation, preparedness, response, and recovery, We have crossed the critical threshold. We're officially in the response phase. Usually, human dispatchers get completely overwhelmed by the flood of emergency calls. Systems break down. But AI? AI actually thrives in this chaos.
Split-second logistics save lives. The AI handles asset allocation, instantly predicting the hottest zones of need and pre-deploying fire crews and ambulances to staging areas before the calls even come in. It uses dynamic rerouting, digesting live road obstruction updates so first responders avoid flooded or blocked paths. And it executes grid balancing. It literally creates intelligent energy islands, shedding non-critical industrial energy loads just to guarantee that hospitals and emergency centers stay online, no matter what happens to the rest of the grid.
Which brings us to Phase 4, Rapid Post-Event Assessment Visual Intelligence. The storm clears, the immediate danger passes, and we transition into the aftermath.
So the crucial point here is how AI completely eliminates the usual post-storm bottlenecks. The system uses advanced computer vision to automate the comparison of pre-event and post-event aerial imagery captured by drones and satellites. It can literally classify damage severity for over 10,000 buildings in mere minutes. This isn't just some cool tech trick, it's a vital administrative tool. It lets insurance companies and governments release emergency funds to affected citizens exponentially faster than ever before.
And finally, Phase 5, the circular economy, optimizing urban metabolism. Rebuilding is all about optimizing resilience, and that means rethinking the very waste left behind by the disaster.
A major disaster leaves behind a massive amount of debris. The traditional method for dealing with this is incredibly labor-intensive, slow, and frankly, super inefficient at sorting usable materials from trash. But the new method? It uses AI-enabled robotic arms. It's a real game-changer that highlights the immense power of digital systems over manual sorting.
Guided by computer vision, these robotic arms can identify and snatch up plastics, metals, and paper at lightning speed. And they do it with a staggering 99% accuracy rate. 99!
This beautifully cyclical process ensures that a disaster's destruction actually paves the way for recovery. Digital sorting turns municipal waste streams right into high-purity raw material feedstocks. So instead of piling debris into a landfill, the very waste left behind becomes the physical, recycled building blocks used to construct a smarter, more resilient city.
From mapping invisible heat to catching the whispers of an incoming storm, guiding emergency responders, and literally rebuilding from the rubble, AI is the foundation of the future city. Which leaves us with one incredibly provocative question. Is your city's digital twin ready for the next storm? Take a look at your own local infrastructure, because the future of urban resilience is already here. Thanks for joining me on this explainer, and keep learning.